Great. So now I'm going to actually start talking about some specific Markov chains. But before I do that, let me make one definition and proposition. So we'll say that a Markov chain P is reversible with respect to some distribution pi, so a distribution so pi is a distribution on the state space if for all states x and y we have that pi of x times the probability of going from x to y is equal to pi of y times the probability of going from y to x. Okay? So this is an important class of Markov chains that ends up having nice properties when you say, like, maybe you want to understand mixing times. But here we're just going to use this simple proposition, which is very easy to prove, which is if P is reversible with respect to pi, is reversible then pi is stationary. So pi P equals pi. And remember, this notation means we view pi as a row vector indexed by the states. P is a square matrix with rows and columns indexed by the states. And then this equation is just saying that pi is stationary. Okay, and why is this? Well, it's a very simple proof. So we're going to say that the sum over all states x of pi of x P of xy. Okay, well, this is going to be what we want here, except it's the y entry of this vector, right? So this is a vector, and the y entry is this. And this is, well, it's the sum over x in x. So because it's reversible, we can say this is the same as pi of y P of yx. But now the x only appears here in the summand, and so you can sort of factor out the pi of y and say, okay, well, this is just the sum over x of the probability of going from y to x. So it's like saying, if you're at state y, what is the probability of going somewhere? Well, you have to go somewhere, so the probability is 1. So this is just going to be pi of y. And so this is the y entry of this vector, and this is the y entry of this vector, and so they're the same. Okay, so this gives us a useful way of checking that some distribution is actually stationary. Like if we have a guess for what the stationary distribution should be, then we can just say, oh, maybe it's reversible, so we'll check this easy equation here. And if we check that and it works, then it is actually the stationary distribution. Okay. So let me give an example. So let's let our state space be the set of integers from 0 to n. Okay, and we'll define a birth and death chain. So a birth and death chain on x. So okay, is a Markov chain on x. In which I'll just say each transition changes the value of the state by at most 1. Okay, so all this is saying is you have your states, which maybe I'll represent by some circles. So I have like 0 here, and then I have 1 here, and then I have 2 here, and so on. Maybe I'll just say n is, I don't know, 3. And I'm just saying that at each step you can go 1 space to the left or 1 space to the right, or you can stay still. You can't jump more than that. So in general, how are we going to define a birth and death chain? Well, we just have to specify the different probabilities of hopping. So I'm going to say, let's let, so I'm going to let P of xy be, we'll call it little piece of x, and this will be if y is x plus 1, and then we'll have little q's of x if y is x minus 1, and then there will be r sub x if y equals x. So p sub x is the probability, like if you're at state x, p sub x is the probability of moving 1 step to the right, q sub x is the probability of moving 1 step to the left, and r sub x is the probability of staying still, and then those are the only things that you can do. So we need p sub x plus q sub x plus r sub x to be 1. So like in this example, the probability of staying here would be r0, this would be r1, r2, r3, but then we also have p sub 0, p sub 1, p sub 2, and then we can go backward with q3. This would be q2 and q1. Okay. And that's the whole transition diagram for this when n is 3. Okay, let's assume that all of the p's and q's are positive. That just makes sure that this is an irreducible Markov chain, right? We don't want a situation, I guess, where like if p1 was 0, say, then like once you're on this side, you wouldn't be able to make it over to these states over here. So you want all the p's and q's to be positive. Okay, let's see. So we're gonna guess the stationary distribution, and we're going to show that this is actually reversible. So, okay, what we want for solving this equation here is we want pi of x times the probability of going from x to y to be the same as, or so here, I should say going from x to x plus 1, this should be the same as pi of x plus 1 times the probability of going from x plus 1 to x, which is q sub x plus 1. Okay. I guess, okay, you also have to check this equation when x and y are not adjacent, like if they differ by 2 or more, but then it's obvious because these are both 0. Yes.
Sorry, did you say that in all birth and death chains that you need to be able to move like that?
I guess, okay, maybe in the definition I'll say they can be anything, like the p's could be 0, that's fine. But I think, let's assume right now that the p's and q's are positive so that we have an irreducible Markov chain, and then it has a unique stationary distribution. Okay, so we can solve this recursively. So I'm going to let w sub x be the product from I equals 1 to x of p sub I minus 1 divided by q sub I. Okay, well then, this means that w sub x, p sub x is w sub x plus 1, q sub x plus 1, right? So you can just check that this works, right? Like here you're saying, take the product of this up to x, and then multiply by an extra piece of x, and then here, okay, you'd have well, okay, let me just write it out. This is, the product from I equals 1 to x of p sub I minus 1 over q sub I, but then times there's a piece of x, and this is the product from I equals 1 to x plus 1, p sub I minus 1 over q sub I, and then there's an extra q sub x plus 1, and you can check that these are the same. Okay, so that means that Wx basically is our stationary distribution, or in other words, P is reversible with respect to this distribution. And if we want it to be a probability distribution, we just need to normalize so that all of the probabilities sum up to 1. So then the stationary distribution, so stationary probability distribution is, well, I'll call it pi, is given by pi of x is just Wx divided by the sum over all states x and x. Oh wait, no, I shouldn't use x. Let's say sum over y of wy. And so here I just have to divide by the sum of them so that sum them up I get. So. Okay. Okay. So now let me define another Markov chain. So let's let G be, let's say, a finite graph. So G has a bunch of vertices and some number of edges. It could have like multiple edges, meaning you could have maybe 2 or 3 or more edges between the same pair of vertices. And I'll also let it have loops. That's also fine. And what I want to do is define the simple random walk on G. So I think I mentioned this maybe on the first day, but I'll define it here again. So the simple random walk. Oh, maybe I should, okay, let's say with vertex set V. So the simple random walk SRW on G is the Markov chain with the state space will be V, where I'll just say we move across a uniformly random edge at each step. Well, I'll say incident edge at each step. Okay, what do I mean by this? Well, okay, so we're at some vertex. There are some edges that are incident to that vertex. I'll choose one uniformly at random so they all have the same probability of being chosen, and then I'll just walk along that edge. So as an example, maybe I have so I gave an example like last week, but here's another example. I have my graph with 4 vertices, and if I'm on, say, this state here, so maybe this is where I am at some time, then there are 4 edges incident to it, so I pick one where each one gets chosen with probability 1/4, and I would walk, maybe I pick this one here, so I walk along there, and now I'm here, and then I do the same thing again for the next transition. Okay. So what is the stationary distribution here? Well, this is just going to be in terms of the degrees of the vertices. So the degree of a vertex is just the number of edges incident to it. Right? So here the degree is 2, degree 2. This one has degree 4. This one has degree 4. And this one has degree 4. Okay. And so the claim is that, oh, okay, maybe I'll assume it's connected. Okay, let's just assume it's connected, and that guarantees that this is actually an irreducible Markov chain. If you had multiple connected components of the graph, then you'd have to be stuck in one of those connected components. So stationary distribution is given by, well, pi of some vertex x is going to be the degree of x. And then let's normalize by just summing over all the degrees. So sum over y in the vertex set of the degree of y. Again, this is just a normalization factor to make sure that the probabilities sum up to 1. But the point is that the probability of being at a certain vertex is proportional to the degree of that vertex. Okay, and why is this? Well, we can just check that it's reversible with respect to this this distribution. So if I have 2 vertices x and y, if they're not adjacent, then these are both 0. So then that's fine. And if they are adjacent, so if x and y are adjacent, then, well, if I take the degree of x, okay, divided by, like, the normalization factor doesn't really matter, but let's just write it. If I take this times, well, the degree of, or the probability of going from x to y, what's the probability of going from x to y if they're adjacent? Well, it's 1 over the degree of x. And we want this to be equal to, well, the right-hand side is pi of y. Times the probability of going from y to x, which is, if they're adjacent, it's 1 over degree of y. And of course, these are equal. Oh, maybe, sorry, I shouldn't be writing y. This is bad. This should be, let's call it z. Any questions up to here? Okay. So now, let me define another Markov chain. So this will be the adjacent transposition shuffle. So for this, imagine you have a deck of cards. The cards are all distinct, and you want to shuffle it. And this is a very inefficient way of shuffling it, where at each step you pick 2 consecutive cards, so 2 cards that are right next to each other, and you swap them, and you just keep doing this over and over. So it's much less efficient than doing like a riffle shuffle or any other kind of thing like that. but we can still study it mathematically and say like, okay, you know, can we understand like how long it takes to shuffle in some sense, and maybe we'll talk about that later when we get into mixing times. But for now, okay, what is the adjacent transposition shuffle formally in mathematical terms? Oh yeah.
Is there a question about previous examples?
Yeah.
Here you have an example using a directed graph, but can I interpret the previous example as a directed graph and use similar exponential? Is it reversible?
Oh yeah. Okay. So well, if it's a directed graph, right? So you're saying here it's undirected, and this is fine. Well, if it's directed, and I had like, let's see, maybe. Something like this, then, so I want to interpret this by saying like the probability of going from 1 to 2 would be 1, and the probability of going from, oh, I see. Wait, maybe I want to not do that, that's stupid. Maybe, okay, I have something like this. So the probability of going from 2 to 1 is now a half. So then, if I want to take the degree, well, okay. Are you asking if the degree will still be the stationary distribution?
Yeah, I'm wondering if this works if you put this as a directed graph.
Right, so I guess if I take maybe I would want it to be the out degree. So if I take the out degree here, then that would be like 1 time, and then okay, I want to take the probability of going from there to there would be 1 over 1, and that should be equal to the out degree here. Yeah, so okay, yeah, then the out degree would be 2 times a half. Yeah, so I think this still works. Right, I think you can do the same thing if you take degree to be out degree, like the number of edges during out.
And for this case, we're not allowing loops, like the path that goes from one branch to the side, or directed graph.
Oh, like a loop.
Yeah.
Oh, I see. I think you can have a loop. So, yeah, you should be able to take a loop where you just interpret it as like adding 1 to the out degree.
Okay. So then can I understand the first example as like a special case?
Oh, I see. I think okay, so yes, if, like I guess here, I was assuming that each time you choose an edge, it's uniformly chosen among the edges. So it would be the same thing if like, if you set the P's and Q's to be appropriate, so that, right, like you want here, like P0 would be a half and R0 would be a half, so that it's like a uniform choice. I guess the point is like, you can have like random walks on a graph where you can choose the probabilities of crossing edges in some crazy way, but usually, I mean, one common thing that people will study is simple random walk, and there they just mean choose it uniformly, which is like the simplest case that you could want. Okay. Yeah, so also, I mean, what I'm about to explain, the adjacent transposition shuffle, is also the simple random walk on a graph. But then I'll generalize it to something that is not a simple random walk because I'm going to bias the probabilities. Okay, so what I want to do is take my deck of cards, but I want to view it as just a permutation of the numbers from 1 to n. So imagine labeling the cards with the numbers from 1 to n, and then some arrangement of the cards is just a permutation. And my transition is going to say, choose 2 adjacent numbers uniformly at random and swap them. So the adjacent transposition okay, maybe what I should have said to this question is that, like, Markov chains in general can be seen as or if you have a finite state space, your Markov chain is a random walk on a graph with some various probabilities associated to the edges, and that's just like the transition diagram that I've been drawing. So like you take any Markov chain, you represent its transition diagram, that's like a graph, it's a directed graph with probabilities associated to it. So here we're just looking at special cases that might be of interest, like if it's a simple random walk. Okay, so the adjacent transposition shuffle is a Markov chain on Sn, here, the symmetric group of permutations of size n, where we choose two adjacent numbers uniformly at random, right? So there are n-1 pairs of adjacent entries in my permutation. I just choose one of them, and they each have probability 1 over n-1 of being chosen. So I choose two adjacent numbers uniformly at random and swap them. Okay, so for example, maybe my permutation, maybe n is 6, and I have something like 4, 1, 3, 2, 5, 6. And maybe for the first step I choose these two numbers. So I swap them and get 4, 3, 1, 2, 5, 6. And then I do something again. Maybe this time I choose the 5 and the 6 and I swap them. 4, 3, 1, 2, 6, 5. And then I just keep going. So this is a simple random walk on a graph, because you can define a graph. So I guess one way of saying this is you define a graph where the vertices are the permutations of size n, where two are adjacent if they differ by just swapping two adjacent numbers. And then this is exactly the simple random walk on that graph. Another way of thinking about that graph is it is the Cayley graph of the symmetric group generated by the adjacent transpositions. So I'll just remark that this is the simple random walk on the, I'll say the right Cayley graph of Sn generated by these transpositions 1, 2, 2, 3, 3, 4, all the way to n-1. Okay. Okay, well, because it's the simple random walk, we know what the stationary distribution is. It's, well, each, the probability of a state is just proportional to its degree. All of the degrees of this graph are n-1, so it's an n-1 regular graph. And so here the stationary distribution is uniform. So I'll just say, and this makes sense because like there shouldn't be any difference between two different permutations. Like why would one permutation have a higher probability of being, or why would you have a higher probability of being at one permutation rather than some other permutation? So it makes sense that the stationary distribution is uniform. So I want to generalize this, and I'll tell you about the biased adjacent transposition shuffle. So for this, I want to fix some probability p, let's say between 0 and 1. And what I want to do is say, okay, again, my state space will be Sn, and again, whenever I want to do a transition, I'm going to choose two adjacent numbers uniformly at random. So each pair has probability 1 over n minus 1 of being chosen. But now, you can see when I swap two numbers, I'm either sorting them into like increasing order, so I'll say I'm sorting them if I'm putting them into increasing order, and I am unsorting them if I'm putting them into decreasing order. So actually these two swaps were both unsorting, so here I put 3 and 1 out of order, so that was unsorting them. Here I put 5 and 6 out of order, so I was unsorting them. But if I were to take, say, the 4 and 3 and swap them, then I would be sorting them. So what I want to do is, okay, so again, state space is Sn. And again, I'm going to choose two adjacent numbers uniformly at random. And now, oh, I should also say, okay, I'll also consider it to be sorting them if they're already sorted and I keep them in order. And if they're already out of order and I keep them out of order, then that's also unsorting. So what I want to do is sort these two numbers with probability p. And then I will unsort with probability 1 minus p. Okay, so let me explain what I'm saying here. Let's say I take some permutation of size 6 like before, so maybe I take my 4, 1, 6, 3, 5, 2, and I pick two adjacent numbers uniformly at random, so maybe I pick the 6 and the 3. And what I'm going to do is, maybe I have a biased coin that has probability p of landing heads, and it has probability 1 minus p of landing tails. So once I've chosen my adjacent numbers, I flip my coin, and if it comes up heads, I put them into increasing order, and if it comes up tails, I put them into decreasing order. So maybe here, if I got tails when I flip my coin, then they're already in decreasing order, so I would just do nothing. Okay. Okay, so let's try to understand, is it clear the definition? Are there any questions? Okay, so let's try to understand the stationary distribution. Well, okay, intuitively, what should we expect the general properties of the stationary distribution to be? Well, it should depend on this number p, right? And if p is very close to 1, then most of the time you're going to be sorting, which means that most of the time you should be staying around the identity permutation, the one that's in increasing order. So if p is very close to 1, you should expect most of the mass of the stationary distribution to be focused or concentrated around the identity permutation. And then on the other hand, if p is very close to 0, most of the time you're unsorting, so you should expect most of the mass of the stationary distribution to be around the decreasing permutation. But also, if p is a half, then we're just going to be getting, what do I want to say if p is a half? Well, okay, it's not exactly the same as the simple random walk, but it's sort of a, it's a variant of it where you're allowed to stay still at some places. This is called a lazy simple random walk. And there the stationary distribution also ends up being uniform. So it turns out that when p is a half, the stationary distribution, Okay, so it'll again be uniform. So let's try to show actually that this is, I guess I have space here. Let's show that this is reversible. So again, I want to satisfy this equation with some guess for what my stationary distribution is. And I claim that I want pi of x to be, well, let's guess that it's some constant raised to the number of inversions of x. So an inversion of a permutation is just a pair of numbers that are out of order. Right? So if you have the increasing permutation, it has 0 inversions because none of the pairs are out of order. If you have the decreasing permutation of size n, then it has n choose 2 inversions because any pair of them are out of order. And I claim that I want something like this, except I'm going to have to take a normalization factor later, but let's worry about that later. Okay, so we're going to take pi of x to be some number to the number of inversions of x, and let's try to guess what this, so I guess just believe me that it will have something like this form, and we're going to try to figure out what lambda is. Well, I want to say that, so we want to have that pi of x, so some number to the number of inversions of x, times the probability of going from x to y equals the same constant to the number of inversions of y times the probability of going from y to x. Okay, well, if x and y are not adjacent in this Cayley graph, or in other words, they don't differ by an adjacent transposition, then these probabilities are both 0 and we're fine, so we can assume that they differ by an adjacent transposition. And so okay, we can assume x and y differ by an adjacent transposition. Oh, I guess you also have to say, well, what if x equals y? The x equals y case is obvious. Okay, but let's assume they differ by an adjacent transposition. And without loss of generality, let's say that x is the sorted one and y is the unsorted one, meaning that for these two numbers where they differ, they are in the increasing order in x and they're in decreasing order in y. So without loss of generality, x is, I don't know, I'll just say more sorted than y. Okay. So then what I want here is to say, maybe I can. So what I want is lambda to the number of inversions. Well, okay, maybe I should also note that if you have this, then the number of inversions of y is just one more than the number of inversions of x. Because I've taken, to get from x to y, you just take two adjacent numbers and you put them out of order, and this creates exactly one additional inversion in the permutation. So what we want is for lambda to the number of inversions of x times the probability of going from x to y to be equal to lambda, well, now the number of inversions of y is the number of inversions of x plus 1 times the probability of going from y to x. But I'll just cancel a lambda to the number of inversions of x from each side, and this just becomes a lambda. Okay? Yeah?
Wait, sorry. So how is inversion y equal to inversion x plus 1 if x is more sorted? Because couldn't, like, flipping a transposition also affect whether or not it's sorted in comparison to, like, the other things?
Well, so it ends up not. Maybe I'll give an example. Yeah, so like, I don't know, maybe I have my permutation from before, 4, 1, 6, 3, 5, 2. If I take just two numbers and I just swap them well, of course, I'm creating an inversion among those two numbers. Or, well, okay, here I'm deleting an inversion. Maybe I should have started with this.
Oh, right, because they have to be adjacent. Okay,
Right, it's because they're
I
adjacent.
see.
Yeah, exactly. Yeah, if you swap just any two numbers, then that could
Yeah,
create
yeah.
a bunch of, you could do something crazy. But yeah, if they're adjacent, then it only creates exactly one inversion.
That makes sense.
Sorry, could you also explain how to define inversion?
How to define inversion, you
Yeah,
said?
what do you mean by inversion?
Yeah, so, okay. Where did I write inversion? So, an inversion of a permutation, maybe I'll call the permutation W. So W here, like if I want to think of it formally, it's a bijection from the set of integers from 1 to n to itself. So about an inversion of a permutation is a pair I comma j such that 1 is less than or equal to I is less than j is less than or equal to n. So these are integers between 1 and n. And okay, I guess, well, it doesn't matter what let's just say, okay, and W inverse of I is greater than W inverse of J. So what this is saying, I'll just give an example. Maybe I'll do a smaller example. For 1, 3, 2. So I want to say that this is just saying that I is less than J, but I appears after J in the permutation. So here are the inversions. Let me use color. The inversions would be 1 and 2. And so I have 1, 2 is an inversion. Or no, sorry, not 1 and 2. 2 and 3. Okay. 2 and 3 is an inversion. 2 and 4 is an inversion because they're out of order. And 3 and 4 because they're also out of order. And 4 and 1 also. And is that it? I think 1, 2, 3, yeah. Okay. Is that clear? Okay. And yeah, so the point is that whenever you multiply by an adjacent, or yeah, whenever you swap two adjacent numbers, you change the number of inversions by exactly 1. Either you increase the number of inversions if you're unsorting, or you decrease the number of inversions if you are sorting. Okay, so now if I go back to this, I wanted, let me rewrite this here, P of yx. Okay. And let's see, I was assuming that x is like the sorted one between these two, which means that, well, what is the probability of going from x to y? Well, they differ in two adjacent numbers. So in order to go from x to y, first I have to choose those numbers, which has probability 1 over n minus 1 of occurring. So maybe I'll, so this here is 1 over n minus 1 times, okay, well, once I've chosen those numbers, I have to unsort them, and that happens with probability 1 minus p. Okay. On the other hand, if I'm at y and I want to go to x, again, I have to choose those particular two numbers to be the ones that I swap. So the probability of that is, again, okay, I'll just say this is lambda times, well, okay, again, I have a 1 over n minus 1 chance of choosing those particular numbers that I need to swap. And then I have to sort them, and that happens with probability p. So now I can solve for lambda. I say, okay, well, let's cancel the 1 over n minus 1 and find that lambda is, okay, lambda should be 1 minus p over p. Okay. So in summary, pi of x for any permutation x should be, well, it's going to be 1 minus p over p, it's the number of inversions of x, but then I need to normalize it just so that it's a probability distribution. So now this is going to be the sum over all permutations w and Sn of, oh sorry, this is not x, this is number of inversions of x. And then this is 1 minus p over p, number of inversions of w. But again, like the numerator is what really matters, and then the denominator is just the normalization factor to make everything nice. Okay. Maybe, okay, this isn't really a Markov chain comment, but I'll just comment, like, what is this thing? Well, this is just a fact about the symmetric group that's easy to prove by induction. So in general, if you take the sum over w and Sn of some number q to the power of the number of inversions of w, this ends up being, well, it's 1, or okay, let's say it's 1 plus q, 1 plus q plus q squared, and so on until plus q plus to the n minus 1. So it has this nice product form. Yeah, maybe as an example, like if I take n equals 3, so for n equals 3, what is this polynomial? If I expand it out, I get 1 plus q squared plus another q, which is 1 plus 2q, and you end up getting another q squared, so that's 2q squared plus q cubed. And this is because there's one permutation of size 3 that has no inversions, which is just 1, 2, 3. There are 2 of them that have one inversion, which are 1, 3, 2 and 2, 1, 3. And there are 2 permutations of size 3 with 2 inversions, which are 2, 3, 1 and 3, 1, 2. And then there's one of them that has 3 inversions, which is 3, 2, 1. So maybe, okay, let me tie this back to Markov chains a little bit. This is like a nice polynomial. It has this nice product formula. And sometimes what people will do is they'll say, okay, we have some Markov chain, some interesting Markov chain, and when we try to normalize the stationary distribution, the denominator is going to be some polynomial, and sometimes it turns out to be some interesting polynomial. And then there are some questions you can ask about, like, well, maybe if I have an interesting polynomial, can I construct a Markov chain where this normalization factor will give me that interesting polynomial in some way? So this is something that you could consider. Yeah.
Can you quickly go over how the summation is equal to that product?
Oh yeah, this is essentially by induction. So what I would do is say, let's assume it's true for n minus 1. Yes, okay. Yeah, assume it's true for n minus 1, and then say, well, how do I get a permutation of size n from a permutation of size n minus 1? Well, I'll take my permutation of size n minus 1, and I'll insert the number n somewhere. And if I insert the number n at the very end, like the last entry, then that's not going to create any new inversions. So that'll be like I've multiplied by 1 here. So I take the polynomial from before. But if I put the number in the second to last position, that'll create exactly 1 inversion and so I'd end up multiplying by q. If I put it in the third to last position, I create two inversions, so I get a q squared, and so on.
Okay.
Yep. Yeah.
You know how we started with the assumption that pi of x equals lambda 2 big thing?
Yeah.
Could you just explain what the intuition behind why we started with that?
Yeah, what is the intuition? I like my intuition is I've seen these things before, and I'm sort of used to knowing that they have that general form. Let me see if there's like a way. I mean, okay, this is maybe not answering your question, but I think a lot of times what you might do, let's say you came up with this Markov chain, no one's ever studied this before, and you say, oh, I want to understand what the stationary distribution is. Well, you could work out either by hand or with a computer what it is for n equals 3 and 4 and 5. For some, you have just some parameter p, and you might start noticing that you're getting these terms that look like this, and you're saying, oh, it looks like maybe the number of, it's some number, and there's like the number of inversions, and this is relevant somehow, and that might lead you to guess that that is the right thing. I don't personally have a better way of explaining the intuition behind why you would expect it to be specifically like number to the power of the number of inversions. I guess, okay, the reason the number of inversions is relevant is because that's like a measure of how close you are to the identity. So if you have this intuition of, well, when p is close to 1, it should be close to the identity, or yeah, close. When p is close to 0, it should be close to the decreasing permutation. That should tell you that it's maybe something having to do with the number of inversions. Whereas, yeah, I don't know exactly how to explain why you would expect it exactly to be like number to the power of the number of inversions, other than like, if you did some examples, maybe you could guess that. Okay. Any other questions? Okay, so these were some Markov chains. We'll talk about more Markov chains later. But let me go back to proving something theoretical about Markov chains. I don't know if I'll have time to, or maybe we'll have time. So what I want to show is the convergence theorem for Markov chains, which just says that, like, let's say you have a finite irreducible Markov chain, so you have a unique stationary distribution, and we want to say that the distribution that you get coming from the Markov chain, saying after some number of steps you have certain probabilities of being in the different states, you want to show that that actually converges to the stationary distribution. Because right now I've just said stationarity means it satisfies some linear algebra equation, but that's not really giving you an asymptotic statement about convergence, so we want to prove that. Let's see. Okay, maybe I'll just give some notation first. So for a random variable, for a sequence xi, I at least 0 of random variables, so a discrete time stochastic process. With finite state space, or taking values in this finite state space, write x in converges to x in distribution. So here, x is some other random variable, and this symbol means that x in is converging in distribution to x if the probability that x in this is an easy definition for if we have a finite state space. So the probability that xn equals x is converging to the probability that that capital X equals little x for all x. And this is convergence and distribution. So this is converging to some random variable, but we might also, and let me stress that this is capital. We might also say xn, or say xn converges in distribution to some measure mu if probability of x in equals x is converging to mu of x for all x. Okay. So now, let me state this theorem. So let's let P be an irreducible aperiodic. So remember, aperiodic meant that we had the periods, and so the period of the Markov chain was 1. So Markov chain on a finite state space X. And so this has a unique stationary distribution, which we'll call pi. Then for any distribution mu on X, we have this equation. Well, okay, I'll say mu e to the I converges to pi. Okay, so the way you think of this is the distribution given by the Markov chain at state I, or at time I. If you started, like your initial distribution for x0, the initial state was mu. So it's like you choose your initial state by sampling according to the distribution mu, and then you run it for I steps. That's going to give you some distribution on your state space, and this will converge to pi. Or in other words, equivalently, if I write my Markov chain like before, where I have just the sequence of random variables x of I, then I'm saying that xi is converging in distribution to this pi, like what I wrote here. Okay. So, before I prove this, let me write a lemma. I won't prove the lemma, but we'll just use this. So if P is irreducible and aperiodic, finite, then there exists some r greater than 0 such that p to the I of xy is greater than 0 for all I at least r, and all states x and y. So if you have an irreducible aperiodic Markov chain, then if you run it for long enough, then the distribution will have, there will be a positive probability of going from any state to any other state if you run it in sufficiently many steps. Okay, so maybe we can prove this. I'll see. So we want to show proof. Or it suffices to show that p to the I of xy converges to pi of y for all x and y. Because this would say that, if you start anywhere, then, and this is converging as I goes to infinity, then your probability of being in y after a long time is converging to pi of y, and so then if you sort of average this result over the distribution mu, then it proves this. So we just have to show this. So this amounts, maybe I'll skip over a detail, but this amounts to showing that p to the I as a matrix is converging entry-wise, so that the entries of this square matrix are converging to some pi, some capital pi, where capital pi is the square matrix whose rows are all pi. So remember, we think of little pi as a row vector, and I'm just saying create a matrix where all of the rows are the same. They're all just that. And so this ends up being the same as what we want to show. Okay. I don't know if I'll have time, but we'll see what happens. So by the proposition, by the lemma, there exists R and some number theta between 0 and 1 such that p to the r of xy is at least 1 minus theta pi of y for all x and y. Right, just because this is saying that you can choose r so that this is positive, and if it's positive, then I can make it, I can choose some theta so that this is so that this is true. Okay, now let's let q be 1 over theta p to the r minus 1 minus theta pi. This might seem a little strange. And what you can note is that the rows of Q sum to 0. In fact, Q is it's the transition matrix of some Markov chain. So Q is the transition matrix okay, so what this means is that if I take Q pi, this is pi. Well, why is that? Yeah, maybe I can write this out. So if I take Q pi of xy, this is just by multiplying matrices, this is going to be the sum over all states z of Q of x z pi of zy. But capital pi of zy, by the definition of pi, it's just little pi of y. Q of xz pi of y. And now pi of y is not in, like, you can factor it out of the summation. And since Q is the transition matrix of a Markov chain, if you sum Q of xz over all z, that's just 1. So this is pi of y, like little pi of y. But that's also the same as the x, y entry of pi, of capital pi. So this is saying that this matrix Q pi is equal to pi. Maybe I'll prove one more step and then we'll just finish it up. I think I probably need like 5 minutes and I have 3, but we'll finish it next time. Okay, so note that p to the r, if I just rearrange the definition of q here, p to the r is 1 minus theta capital pi plus theta q. And what I want to show, so I want to show that p to the rk is 1 minus theta to the k pi plus theta to the k q to the k for all positive integers k. So we already know the k equals 1 case, and I want to prove this by induction on k. And maybe I'll just save this for next time. So we will do this by induction on k, and then we'll finish the proof. So I'll recall the steps here at the beginning of next class. Oh, and I'll post a p-set today, probably within an hour. Yes?
Why is 1 over theta times PVR minus 1 minus theta times pi a transition matrix of Markov?
Oh, let's see. So it's because, did I write this wrong? Well, okay, I guess if you sum up the, okay. Maybe I'll address that at the beginning of next time. Okay.
I think it holds just that those all sum to 1. If you like work out like the thetas and all the entries are non-negative, then that's sufficient.
Yeah.
Okay.
Yeah. So I think it's probably you just have to go through it and check.
Yeah, I just didn't know if it was like obvious.
I think it's not obvious, but like it's something that you can check without difficulty. Yeah. Okay.